The universe is expanding faster than light itself. We are about to journey through 50 cosmic facts that will permanently alter how you see the night sky. By the end of this, you will understand that reality is far stranger than any science fiction. We will uncover worlds of solid diamond, explore storms larger than our entire planet, and even question if everything we know is just a projection. What part of the cosmos most captures your imagination? Our cosmic home is stretching apart at an ever-increasing rate. This was one of the most startling discoveries of the 20th century, when astronomers observed that the light from distant exploding stars was far dimmer than it should have been. These stellar beacons, known as supernova, revealed that galaxies are not just sailing away from each other, they are accelerating. Something is actively pushing the fabric of space itself apart, a mysterious force we call dark energy. Think of the universe as a loaf of raisin bread rising in an oven. The raisins, which are like galaxies, are not moving through the dough on their own. Instead, the dough itself is expanding, carrying all the raisins away from each other. Now imagine the oven suddenly gets hotter, and the dough begins to rise faster and faster. That is the effect of dark energy, a cosmic repulsive force that counteracts gravity. This discovery completely overturned our previous understanding, which assumed the universe's expansion would slow down over time. The ultimate fate of everything now hinges on this invisible driver. If dark energy continues to dominate, one possible future is the Big Freeze, a lonely, cold end where all stars burn out and galaxies become so isolated that their light can never reach one another. An even more dramatic, though less certain, possibility is the Big Rip. In this scenario, dark energy grows so powerful that it first shreds galaxy clusters, then galaxies themselves, then stars, planets, and finally, it would tear apart the very atoms that make up all matter. We are left with a fundamental question that still haunts cosmology. What exactly is dark energy? We know it makes up about 68% of the universe, yet we cannot see it, touch it, or explain its origin. It remains the greatest unsolved puzzle in physics, a ghostly presence dictating the destiny of the cosmos. While dark energy dictates the fate of the cosmos, another profound discovery suggests the universe is also brimming with the potential for life. Drifting near the heart of our Milky Way is an immense cloud known as Sagittarius B2, a region of space spanning an area larger than our entire solar system. Within this vast cosmic nursery, astronomers have detected a staggering substance, vinyl alcohol. The cloud holds enough of this complex organic molecule to create billions upon billions of liters of pure alcohol. This is not the kind you would find in a beverage, but its existence is no less intoxicating for scientists. How does such a complicated molecule form in the cold, empty void between stars? The process begins inside ancient stars, where nuclear fusion forges simple elements like carbon and oxygen. When these stars reach the end of their lives, they expel these elements into space. In the dense, cold environment of a molecular cloud like Sagittarius B2, these atoms can stick to tiny dust grains. There, shielded from harsh radiation, they slowly link together through chemical reactions, building more complex structures atom by atom until molecules like vinyl alcohol are born. Finding such a sophisticated organic compound floating freely in space is a revolutionary clue. It tells us that the fundamental ingredients for life, the very building blocks, are not unique to Earth. They are being manufactured in great abundance throughout the galaxy, scattered by stellar winds and supernova explosions. This cosmic brewery suggests that wherever conditions are right, the raw materials for life are likely already present, waiting. The universe, it seems, is not only expanding but also prepping the kitchen for a feast. Our galaxy's vast chemical factories are not the only place where the universe defies common sense. The planet Venus presents a temporal paradox that challenges our very definition of time. On this world, a single day lasts longer than an entire year. It takes Venus 243 Earth days to spin just once on its axis, a lazy, slow rotation. Yet it completes a full journey around the Sun in only 225 Earth days. This means if you could stand on its scorching surface, you would celebrate your birthday before you witnessed a single sunrise to sunset. The reason behind this backward clockwork is one of the solar system's great mysteries. Most planets spin counterclockwise, a legacy of the spinning disk of dust and gas that formed them. Venus, however, spins clockwise in what is known as a retrograde rotation. One leading theory suggests that in the solar system's violent youth, a colossal object, perhaps as large as a small planet, slammed into Venus. This titanic impact could have literally stopped the planet in its tracks and sent it spinning the wrong way, dramatically slowing its rotation in the process. Another possibility is that the Sun's powerful gravitational tug on Venus's thick atmosphere created tides that gradually slowed and eventually reversed its spin over billions of years. This bizarre rotation creates a day-night cycle unlike any other. From a single spot on Venus, you would see the Sun rise in the west and set in the east, but you would have to wait for nearly 4 Earth months between each sunrise. The planet's strange spin serves as a profound reminder that the rhythms we consider universal are merely local, and that elsewhere, time itself can flow to a completely different beat. If you think Venus has a strange relationship with time, wait until you encounter a neutron star where matter itself is pushed to its absolute limit. These stellar corpses are so incredibly dense that a single sugar cube-sized piece of one would weigh about 1 billion tons here on Earth. That tiny fragment would possess the same mass as a mountain, all compressed into a speck you could balance on a fingertip. This almost unimaginable density is the final chapter in the life of a massive star. When such a star runs out of fuel, it can no longer support its own immense weight against the crush of gravity. Its core collapses in a fraction of a second, triggering a cataclysmic supernova explosion that blasts its outer layers into space. What remains is a neutron star, an object typically only about 12 miles across, yet containing more mass than our entire Sun. All that star stuff is compressed into a sphere so small it could fit inside a city. The force of this collapse is so extreme that it forces electrons and protons to merge, transforming nearly all the star's matter into a solid ball of neutrons. The surface of such an object is a realm of bizarre physics. It is a perfect crystalline crust, harder than any substance known, floating on an ocean of superfluid neutrons. Even the topography is alien. Any imperfections on this surface, what we might call mountains, are only millimeters high. Yet because the material is so unimaginably dense, these tiny bumps, no taller than a pencil lead, would hold the mass of entire terrestrial mountain ranges like the Himalayas. This is a place where the very rules of reality are rewritten by gravity's ultimate victory. The crushing density of a neutron star is not the only way the universe forges impossible materials. Orbiting a star 40 light-years away is a world that transforms celestial chemistry into pure treasure. The exoplanet 55 Cancri E is a super-Earth, a world twice our planet's size and 8 times its mass, and it is thought to be a planet of diamond. How could an entire world become a jewel? The secret lies in the planet's composition. Astronomers discovered that its parent star contains an unusually high amount of carbon, the same element that makes up coal and, under the right conditions, diamond. They believe that as this planetary system formed, 55 Cancri E coalesced from this carbon-rich material. Under the immense pressure from the planet's own powerful gravity, that carbon was compressed into a crystalline structure, creating a layer of diamond that could be hundreds of miles thick. This is not a peaceful, glittering paradise, however. The planet orbits so close to its Sun that a single year passes in just 18 hours. This proximity creates a world of fire and ice in the most extreme sense. One side of the planet is permanently locked in scorching daylight, with surface temperatures soaring to over 4,000 degrees Fahrenheit, hot enough to melt rock and vaporize metal. The other side is trapped in eternal, frigid night. If you could stand on the day side, you might witness a landscape of solid diamond, glowing with a hellish incandescence under the light of an enormous nearby star. This world of extremes forces us to reconsider the very definition of a planet. It is a reminder that the universe is a master alchemist, capable of turning the most common elements into realms of breathtaking and terrifying wonder. That diamond world's hellish permanence is a testament to alien environments, but even our own moon holds a record of human presence that is almost eternal. The footprints left by the Apollo astronauts are not fading. They are etched into the lunar soil with a permanence we can scarcely comprehend on Earth, and they will likely remain undisturbed for millions of years. This incredible longevity is a direct result of the moon being a world frozen in time. Our satellite has no atmosphere to speak of, which means there is no wind to whisper across the surface and smooth over the impressions. There is no flowing water to wash them away, no rain to fall and erode their sharp edges. The moon is also geologically dead. Its internal fires went out long ago, so there are no earthquakes or tectonic shifts to churn the soil and bury these historic marks. On our dynamic Earth, a footprint on a beach is gone with the next high tide. A path through a field is reclaimed by grass in a single season. But on the moon, the only force that works to erase these footprints is incredibly slow and subtle. It is the constant, gentle rain of micrometeorites, tiny specks of cosmic dust that strike the surface over eons, gradually churning the top layer of soil in a process scientists call gardening. Yet this process is so gradual that it would take tens of millions of years to fully erase a crisp boot print. This creates a profound thought for the future. One day, long after our cities have turned to dust, these silent steps in the sea of tranquility will remain as our most enduring monument. They await future lunar archaeologists, beings who may one day gaze upon these patterns and piece together the story of a species that first reached beyond its home world, leaving a signature in the dust that outlasts mountains. While the moon preserves our past in silent dust, Mars boasts a monument of raw planetary power so grand it defies all earthly scale. Olympus Mons is not merely a mountain. It is the largest volcano in the entire solar system, a shield volcano so colossal it would blanket the entire state of Arizona. From its base on the Martian plains to its summit, it towers 16 miles high, making it nearly 3 times the height of Mount Everest. If you stood at its peak, you would not see the curvature of Mars. You would be above the planet's atmosphere, looking down into space. Its formation is a story of planetary patience and a world that gave up. Unlike Earth, Mars lacks active plate tectonics. On our world, the crust is a fractured jigsaw puzzle of shifting plates. When a hot spot of magma pushes up from the mantle, it can create a chain of volcanoes like the Hawaiian Islands as the plate slowly moves over the stationary plume. But on Mars, the crust is a single, immobile shell. For billions of years, a single, incredibly persistent magma plume kept rising to the exact same spot, layer after layer of lava slowly cooling and solidifying, building the volcano upward and outward without interruption. This created its characteristically flat, gently sloping profile, like a warrior's shield laid upon the ground. This lack of tectonic movement allowed Olympus Mons to grow to such an incomprehensible size. It is a testament to a world that was once geologically alive, building a single, magnificent feature for eons until its internal fires finally cooled. This Martian giant stands not as a symbol of violence, but of quiet, relentless accumulation, a geological record of a planet's enduring, if ultimately finite, ambition. Far beyond the quiet reign of Neptune, in the cold and sunless depths of our solar system, a ghost may be pulling the strings. The orbits of several small, icy worlds out in the Kuiper belt are clustered and tilted in a way that defies easy explanation. They seem to be herded, their path subtly guided by the gravitational influence of something massive, something we have never seen. This is the compelling evidence for a hypothetical giant, a world astronomers call Planet 9. This would not be a small, rocky body like Pluto, but a true planet potentially up to 10 times the mass of Earth, tracing an enormously elongated path around the Sun. A single year on this world could last 20,000 Earth years. The search for this phantom planet is one of the greatest modern astronomical detective stories. Researchers are not looking for a bright pinprick of light. At such a tremendous distance, perhaps 20 times farther from the Sun than Neptune, it would be incredibly faint, reflecting only the barest sliver of sunlight. The challenge is like trying to spot a single piece of coal in the vast blackness of a moonless night, using only the faint glow of a candle held miles away. Telescopes scan these remote stretches of space, taking images of the same patch of sky over weeks and months, searching for one tiny dot that moves ever so slowly against the backdrop of fixed stars. But what could Planet 9 be if it is truly there? One fascinating theory suggests it was not born in this frozen outskirts but was an exiled giant. In the solar system's chaotic early days, gravitational interactions with Jupiter or Saturn could have slingshotted this world from the inner system, casting it out into a lonely, sprawling orbit where it has silently drifted for billions of years. Finding it would be more than just adding a new world to a textbook diagram. It would rewrite the history of our own cosmic neighborhood, revealing a dramatic past of planetary pinball and gravitational upheaval. The very existence of this hidden giant would force us to look at the familiar planets not as fixed landmarks, but as survivors of a much more turbulent and dynamic creation story. Our search for hidden giants like Planet 9 reminds us that the true ruler of our solar system has been in plain sight all along. Every single planet, from tiny Mercury to the gas giant Jupiter, is utterly dwarfed by the Sun. This star alone contains 99.86% of all the mass in our entire solar system. Picture every world you have ever heard of, every moon orbiting Saturn, every asteroid tumbling in the belt, and every distant comet. If you could place all of it together on one side of a cosmic scale, the Sun on the other side would outweigh it more than 700 times over. To visualize this staggering imbalance, imagine a professional bowling ball, dense and heavy. Now sprinkle a few dozen individual grains of sand around it. That bowling ball is the Sun, and those tiny, almost weightless specks are everything else. This overwhelming concentration of mass is the reason for its absolute gravitational authority. Every object in our system, from the Earth you stand on to the Voyager probes now in interstellar space, is tethered to this colossal anchor by an invisible leash. It dictates every orbit, commands every path, and holds the entire cosmic architecture in its sway. This is not a partnership of equals, it is a monarchy with a single, brilliant star as its sovereign. Without this central anchor, our solar system would simply fly apart, its worlds scattering into the dark like lost marbles. This immense gravity also creates the extreme pressure and temperature at its core necessary to ignite nuclear fusion, the process that transforms matter into pure energy and gives us light and heat. The Sun is not just another object in our sky, it is the stage upon which our entire existence is performed, a titan whose quiet, constant burn makes life itself possible. Even the Sun's immense gravity will one day be defeated by a force no bigger than an electron. After a star like our Sun exhausts its nuclear fuel, it undergoes a transformation more profound than death, collapsing into a white dwarf. This stellar remnant packs the entire mass of a star into a volume no larger than Earth. The density this creates is almost beyond comprehension. A single teaspoon of white dwarf material would weigh as much as a full-grown elephant here on our planet. How can matter become so unimaginably compressed? The answer lies in a quantum mechanical phenomenon known as electron degeneracy pressure. When gravity crushes the star's core, it squeezes the atoms together until the electrons are stripped from their orbits, creating a dense plasma. These electrons, governed by the laws of quantum mechanics, simply cannot be forced any closer together. It is as if you tried to pack an entire stadium of people into a single closet, and they all put their arms out, creating an irresistible pressure that prevents them from being squeezed further. This electron degeneracy pressure is what halts the star's total collapse into a black hole, creating a stable but bizarre Earth-sized diamond. This is not a permanent state, however. A white dwarf has no internal energy source left. It is simply the hot, fading ember of a spent star, and it will spend the next billions upon billions of years slowly radiating its remaining heat away into the frigid vacuum of space. Its ultimate fate is to cool into a cold, dark, crystalline sphere of carbon and oxygen, a black diamond drifting silently through the cosmos. This cosmic cinder represents the final, quiet state for the vast majority of stars, including our own Sun, a patient and chillingly distant future written into the laws of physics themselves. Our Sun's final state as a black diamond is a chilling prospect, but the universe is far from a sterile desert. Water, the very essence of life on Earth, is astonishingly abundant across the solar system. It exists not just as a trace vapor, but as vast frozen reserves and even in liquid form. Our own moon harbors billions of tons of water ice locked in permanent shadow at its poles, inside craters where sunlight has not shone for billions of years. This discovery transforms our lunar neighbor from a dry, barren rock into a potential cosmic oasis for future explorers, who could theoretically mine this ice for drinking water, breathable air, and rocket fuel. But the truly profound reservoirs lie farther out. Jupiter's moon Europa is a cracked, icy world that likely conceals a global ocean beneath its frozen crust. This subsurface sea could hold more than twice the volume of all Earth's oceans combined, kept in a liquid state by the immense tidal forces generated by Jupiter's gravity, which flex and heat the moon's interior. Even more dramatically, Saturn's small moon Enceladus actively erupts. Gigantic plumes of water vapor and ice crystals shoot hundreds of miles into space from fractures in its south pole, a clear sign of a subsurface saltwater ocean. This is not a hidden, silent sea. It is a world that is openly venting its water into the cosmos, offering us a free sample. The presence of liquid water, an energy source, and organic compounds on these moons makes them the most promising places in our solar system to search for extraterrestrial life. We are no longer asking if life could exist beyond Earth, but where. The cosmos, it turns out, is not a dry, empty void. It is dotted with potential habitats, each a miniature world with its own secret ocean, waiting for the day we learn to dive into their depths. Our own moon is in a slow, steady retreat from our world. Each year, the distance between Earth and its companion grows by about 3.8 centimeters, roughly the same rate your fingernails grow. This gentle drift is the result of a celestial tug of war driven by the ocean's tides. The moon's gravity pulls on our planet, causing the oceans to bulge slightly toward it. But because Earth rotates so much faster than the moon orbits, our planet actually spins ahead, dragging that watery bulge with it. This bulge, in turn, exerts its own gravitational pull on the moon, giving it a tiny energy boost that pushes it into a slightly higher orbit. This process is a subtle but relentless transfer of energy, with Earth's rotation slowing down as the moon inches further away. The consequences of this cosmic dance unfold over timescales that dwarf human history. Billions of years from now, our day will be significantly longer. The moon will appear smaller in the sky, and one of nature's most spectacular events, a total solar eclipse, will become a thing of the past. The moon's disk will simply be too small to completely cover the sun, leaving only partial and annular eclipses for any future life to witness. This slow drift redefines our relationship with the most familiar object in our sky. The moon is not a permanent fixture, but a dynamic partner in a billion-year-long dance, gradually changing the very rhythm of our world. That gentle lunar drift is a slow and steady rhythm, but elsewhere in our solar system, weather rages on an unimaginable scale. Jupiter's Great Red Spot is a storm that could swallow our entire planet whole, a colossal, swirling vortex of crimson gas that has been churning for centuries. This is not a temporary squall, but a permanent fixture of the Jovian atmosphere, an anticyclonic storm where winds scream at speeds exceeding 400 kilometers per hour. To stand at its edge would be to witness a wall of clouds towering 5 miles above the surrounding atmosphere, a hurricane so vast that its dimensions are measured in planetary scales. The very fact that we have observed it for at least 400 years since the first telescopes were pointed at Jupiter presents a profound mystery. What could possibly fuel a storm for so long through generations of human history? The secret lies in Jupiter's nature as a gas giant. Unlike Earth, which has a solid surface to disrupt atmospheric flow, Jupiter is a deep, churning ball of hydrogen and helium. The Great Red Spot acts like a massive atmospheric wheel, driven by the planet's immense internal heat and the sheer energy of its rapid rotation. A day on Jupiter lasts less than 10 hours, and this furious spin whips the atmosphere into a complex tapestry of jet streams and storms. The spot is a self-sustaining system, feeding on the smaller storms and atmospheric currents that it constantly consumes. Yet, even this titan is not immortal. Modern observations reveal that the Great Red Spot is slowly shrinking. Measurements from the late 19th century suggested it was wide enough to fit 3 Earths side by side. Today, it is barely large enough to contain one. The reasons for this gradual decline are still debated. It could be a natural, long-term cycle of the storm, or it may be interacting with other jet streams that are slowly eroding its power. Will it eventually vanish entirely, or will it stabilize and persist for another 4 centuries? This slow transformation of a solar system icon reminds us that even the most seemingly permanent features of the cosmos are part of an endless, dynamic dance of creation and dissolution. Even the most violent cosmic events occur in absolute silence. The vacuum of space is a perfect void, an emptiness so complete that sound waves have no substance to travel through. Imagine witnessing a supernova from a safe distance, watching a star tear itself apart in a flash of light brighter than a billion suns. You would see the shockwave of energy ripple outward, a sphere of incandescent gas expanding at a fraction of the speed of light, but you would hear nothing. The universe's grandest explosions play out as the most breathtakingly silent films. This profound silence means that if you were floating beside a colliding galaxy or a roaring stellar nursery, your only senses would be sight and the visceral feel of vibrations through your spacesuit if you touched something solid. The scream of a star being born and the final whisper of a black hole's feast are sensations forever lost to the void. This creates a deeply eerie disconnect between the visual drama of the cosmos and its acoustic reality. We are conditioned by our world where a crashing wave or a clap of thunder comes with its own soundtrack. But out there, the soundtrack is perpetually muted, leaving only the silent, majestic, and terrifying ballet of light and gravity to tell the story. The profound silence of space is matched only by its staggering scale. We often speak of the universe being vast, but one comparison truly makes its immensity tangible. There are more stars in the observable universe than there are grains of sand on every beach and in every desert on our entire planet. This is not a poetic exaggeration, but a conclusion drawn from rough, humbling calculations. Astronomers estimate there are around 200 billion trillion stars in the cosmos we can see. That is a 2 followed by 23 zeros. To put that number in perspective, if you tried to count every single one of those stars at a rate of 1 per second, it would take you thousands of trillions of years to finish. Now compare that to our world. How many grains of sand exist on Earth? If you were to gather every grain from every shoreline, every dune in the Sahara, and every hidden desert, the total is estimated to be around 7.5 trillion. That number is almost too large to grasp, yet it is utterly dwarfed by the stellar census. For every single grain of sand you could hold in your hand, there are over 25,000 suns shining in the void. This means a small handful of sand, the kind a child might let trickle through their fingers at the water's edge, represents more stars than all the humans who have ever lived. This analogy collapses the distance between the intimately familiar and the cosmically grand. The next time you stand on a beach looking out at the ocean, try to hold that thought. The countless grains beneath your feet are a minuscule fraction of the lights in the sky. Each of those points of light is a sun, and many likely host their own families of planets, creating a canvas of potential worlds so immense it forever redefines our place in the grand scheme of things. That immense number of stars hints at countless worlds, each with its own dynamic story of creation and change. Even the planets within our own solar system are far from static, as Mercury so dramatically proves. The innermost planet is actually shrinking. For decades, planetary scientists believed that Mercury, a small, dense world, had cooled and solidified into a permanent, unchanging sphere billions of years ago. But the Messenger spacecraft revealed a planet that is still cooling and contracting today, causing its entire surface to wrinkle and crack. As the planet's massive iron core slowly cools, it solidifies and contracts, pulling the entire world inward. The planet's single, unbroken crustal shell has nowhere to go but to buckle under the strain. This global contraction has thrust up immense cliff-like features that snake across the landscape for hundreds of miles. These are the lobate scarps, towering walls of rock that can soar over a mile high, dwarfing any similar feature on Earth. They are the wrinkles on a drying grape, but on a planetary scale, evidence of a world growing smaller with time. This discovery forced a complete revision of our models for terrestrial planets. We once thought such geological activity was a brief, fiery chapter in a planet's youth, followed by billions of years of quiet. Mercury tells us that even a small, seemingly dead world can continue its slow transformation, its interior still whispering the story of its hot birth as it gradually tightens its own skin. This subtle, ongoing collapse reminds us that a planet's history is written not just in its craters, but in the very folds and fractures of its global surface. Life finds a way to endure in the most hostile environments imaginable. While the silent vacuum of space would kill almost any creature in seconds, a few extraordinary organisms not only survive there, they thrive. These are the extremophiles, and their champion is the nearly indestructible tardigrade, often called the water bear. These microscopic, 8-layered animals can be found in the most mundane places on Earth, from a drop of water on a mossy leaf to the sediment at the bottom of a pond. Yet, they possess superpowers that defy belief. Scientists have exposed tardigrades to the raw conditions of space, with its brutal radiation, near absolute zero temperatures, and complete lack of pressure and air. The water bears did not just die, they entered a state of suspended animation, a metabolic shutdown so deep it is almost indistinguishable from death. They curled into a tiny, dried-out barrel called a tun, and when they were brought back inside a spacecraft and rehydrated, they simply woke up unharmed and went about their business as if their cosmic stroll was a minor inconvenience. They are not alone. Certain bacteria, like the resilient Deinococcus radiodurans, have also been shown to survive for years on the outside of space stations, shielded only by a thin layer of dust. This incredible hardiness forces a radical question upon us. If life can hitch a ride on the outside of a spacecraft, could it have done the same on a natural spaceship, like an asteroid or a comet? This idea is known as panspermia, the theory that the seeds of life are everywhere, traveling between worlds. Imagine a large asteroid slamming into a world like ancient Mars when it might have been warm and wet. The impact could have blasted rocky debris containing these dormant microbes out into the solar system. That debris then travels for millions of years, a cosmic ark carrying its frozen passengers. Eventually, a fragment lands on another young planet like Earth, seeding its oceans with the first building blocks of life. The implications are staggering. It suggests that life may not be a rare, miraculous accident, but an inevitable cosmic process. We, and every living thing we know, could be the descendants of interstellar travelers, our origin story written not in one world, but across the vast star-scattered galaxy. Our own galaxy is on an unstoppable collision course. The Andromeda Galaxy, our closest major galactic neighbor, is hurtling toward the Milky Way at a breathtaking speed of about 250,000 miles per hour. This is not a possibility, but a certainty written in the motion of the stars, scheduled to begin in roughly 4.5 billion years. From a hypothetical future Earth, the approach would be a slow-motion spectacle spanning millions of years. At first, Andromeda would appear as a small, faint smudge in the night sky. Over eons, it would grow, swelling from a hazy patch into a brilliant, structured spiral that eventually dominated the entire heavens. As the two galaxies draw nearer, their mutual gravity begins to warp and distort their classic shapes, pulling out long, shimmering streams of stars and gas in a cosmic dance of titans. The actual merger would be the most dazzling light show in the history of our planet. Stars would not slam into each other in a fiery cataclysm. Space is too vast and stars are too far apart. The average distance between stars in a galaxy is so immense that direct collisions are incredibly rare. Instead, the solar systems would be thrown into new, chaotic orbits, cast like glitter into a newly forming galaxy. Our own sun would likely be flung far from its current position, sailing through a reshaped cosmic environment. The sky would be filled with the glow of countless new stars, ignited as clouds of gas and dust collided and compressed. What will emerge from this billion-year-long embrace? Not two spirals, but a single, massive elliptical galaxy, a vast and relatively featureless island of stars that astronomers have already named Milkomda. This future merger forces us to see our galaxy not as a static island, but as a dynamic entity with a dramatic history and an even more spectacular future, all unfolding on a timescale that humbles human imagination. Gravity does more than just pull on matter, it twists the very fabric of time. Einstein's theory of relativity revealed this stunning truth, that time itself is not a constant river flowing at the same rate for everyone. Near a tremendously massive object like a black hole, time slows down. This effect, known as gravitational time dilation, means your clock ticks slower the deeper you are in a gravitational well. To understand this, picture a brave astronaut on a one-way mission to study a black hole. She is tethered to a distant mothership, and as she plunges toward the event horizon, she continues to send back a steady signal, a pulse of light once every second from her perspective. For her, time feels normal. The seconds pass as they always have, but for the crew watching from the safety of the distant ship, her story unfolds in surreal slow motion. Her 1-second pulses begin to arrive further and further apart. First 2 seconds between pulses, then 10, then a minute. Her approach to the black hole's edge would appear to stretch out over an eternity. The light from her ship would redden and dim, fading to infrared and then to nothing, as if she is frozen in time at the very brink. She, however, would experience none of this slowing. If she could look outward, the entire future history of the universe would flash before her eyes in a final, blinding burst of blue shifted light. This is not a magic trick or an illusion, but a fundamental property of our universe, confirmed by incredibly precise atomic clocks that tick at slightly different rates on the ground compared to satellites in orbit. Near a black hole, this gentle curve in spacetime becomes a profound cliff, separating one person's reality from another's in a rift that is both beautiful and terrifying. The universe possesses not just a single timeline, but a tangled web of them, where gravity is the master weaver. Saturn's north pole holds a secret more perfect than any jewel, a hexagon of clouds so vast it could swallow 4 Earths with room to spare. This colossal 6-sided jet stream is a geometric marvel etched into the planet's atmosphere, a shape that defies the chaotic nature of weather. It is not a temporary feature, but a permanent fixture, churning for decades, perhaps even centuries, with each side longer than our entire planet's diameter. How can a perfect hexagon, a shape you might draw with a ruler, form and persist in a turbulent, gaseous world? The answer lies in a complex interplay of physics. Scientists believe it is a standing wave pattern, a stable ripple in Saturn's atmosphere. Picture a spinning bowl of water. If you spin it just right, the surface will form distinct, stable patterns. Now scale that up to a planetary level. Saturn's rapid rotation, with a day lasting only 10.7 hours, acts like the spinning bowl, while the differing speeds of its eastward jet streams create the conditions for this wave to lock into place. The hexagon is essentially a self-organizing storm, a towering wall of clouds where winds scream at over 300 miles per hour. It is a natural demonstration of fluid dynamics, a pattern that emerges from chaos when the conditions are precisely right. This alien geometry forces us to reconsider what is possible in a planetary atmosphere. It is a reminder that the universe has a hidden love for order, painting perfect shapes on the most unlikely of canvases. Yet the true furnace of our solar system is not the closest world to the Sun. That grim title belongs to Venus, a planet shrouded in clouds that reflect sunlight but trap heat with terrifying efficiency. Its surface temperature soars to a blistering 800 degrees Fahrenheit, hot enough to melt lead and even some spacecraft components. This inferno is a direct result of a runaway greenhouse effect, a process that transformed a world once possibly similar to Earth into a hellish pressure cooker. Venus is wrapped in an incredibly thick atmosphere composed almost entirely of carbon dioxide with clouds of sulfuric acid. This dense blanket allows sunlight to pass through and heat the ground, but when the surface tries to radiate that heat back out as infrared radiation, the carbon dioxide molecules trap it. The heat has nowhere to go, so it builds and builds, creating a surface hotter than that of Mercury, despite Venus being nearly twice as far from the Sun. This planetary oven serves as a stark and sobering cautionary tale. It shows us the ultimate potential of a greenhouse effect left unchecked. While Earth's climate is a delicate, balanced system, Venus demonstrates what happens when that balance is completely lost. Studying our scorching neighbor is not just about understanding another world. It is a vital lesson in planetary stewardship, a glimpse into a possible, extreme future that underscores the profound importance of protecting the fragile atmosphere that makes our own world livable. This cosmic cautionary tale of a runaway greenhouse effect is a reminder of how alien a planet can become. But the early universe may have forged stars from a substance even more exotic than carbon dioxide. The first stars to ever ignite might not have been powered by nuclear fusion at all. A compelling theory suggests they were dark stars, colossal behemoths fueled by the annihilation of dark matter. In the primordial cosmos, dark matter was far more concentrated, forming dense clouds that also pulled in vast amounts of hydrogen and helium gas. At the heart of these clouds, dark matter particles would collide and annihilate, releasing a tremendous and steady outpouring of heat. This process would have prevented the gas from collapsing to the densities needed to spark conventional fusion, creating a star that glowed with a strange, cool light generated entirely by an invisible fuel source. The scale of these objects is almost incomprehensible. A single dark star could have been millions of times more massive than our Sun and billions of times brighter, yet its surface would have been far cooler than a fusion-powered star. This different power source would have fundamentally altered their life cycle. Instead of exploding as supernova after a few million years, dark stars could have shone for millions, perhaps even billions of years, acting as long-lasting lighthouses in the young, dark universe. The hunt for these phantom suns is now a primary goal for the James Webb Space Telescope. Astronomers are scanning the deepest reaches of space and time, looking for the unique infrared signature of a massive, cool object that should not exist according to our standard stellar models. Finding just one would be a monumental discovery. It would not only confirm a new, bizarre type of star, but it would also provide our first direct glimpse into the properties and behavior of dark matter itself. We would finally have a cosmic laboratory to study the universe's most elusive substance, a breakthrough that could unlock the secrets of both the first light and the hidden mass that binds the cosmos together. The hunt for dark stars reveals a universe of bizarre possibilities, but even our own solar system holds worlds that defy the very idea of a surface. You cannot stand on Uranus or Neptune. These distant ice giants are not solid spheres of rock, but worlds without a true surface to land upon. Imagine trying to find footing on a planet that is essentially a deep, global ocean, but one made of exotic, superheated slush. A spacecraft descending into their atmospheres would first encounter thick clouds of hydrogen and helium, much like Jupiter and Saturn. But as it sinks deeper, the environment transforms. The immense pressure and relatively mild internal heat create a unique transitional layer, a slushy mantle of water, ammonia, and methane ices. This is not ice as we know it on Earth, frozen and brittle. Here, under thousands of times the pressure of our own atmosphere, these substances exist in a hot, dense, fluid state, a bizarre, electrically conductive soup. There is no clear boundary where the atmosphere ends and the ground begins, only a gradual thickening into this planetary ocean. Any probe would continue to sink, its instruments reporting back on an increasingly alien world until the pressure simply became too great. Long before it could reach the suspected rocky core at the planet's heart, the spacecraft would be imploded, crushed into a tiny, unrecognizable speck by the weight of the world itself. This structure makes Uranus and Neptune fundamentally different from the terrestrial planets. They are fluid worlds from cloud tops to core, dynamic orbs where the very concept of up and down loses its meaning in a perpetual, pressurized descent. Every star is a time machine sending us messages from the past. The twinkling light from even our closest stellar neighbor, Alpha Centauri, is not a live broadcast. It is a 4-year-old recording traveling across the void at the universe's ultimate speed limit. When you gaze at that star, you are not seeing it as it is tonight, but as it was 4 years ago. This concept, known as look-back time, transforms the entire night sky into a vast historical archive. The deeper you peer into space, the further back in time you see. The light from the bright star Betelgeuse in Orion's shoulder has been journeying for over 600 years. If that star met its explosive end as a supernova just a century ago, we would have no idea. Its final, brilliant flash is still en route to us, a piece of news traveling at the speed of light that has not yet arrived. This effect becomes truly profound when we look beyond our galaxy. The Andromeda Galaxy, a faint smudge to the naked eye, appears to us as it was 2.5 million years ago. Our human ancestors were just beginning to craft stone tools when the light now striking your retina began its epic voyage. The most distant galaxies observed by the Hubble and James Webb Space Telescopes are seen as they were over 13 billion years ago, in the cosmic dawn just after the Big Bang. We are not just looking out into space, we are peering back through eons, watching the universe's childhood play out in the faint glow of ancient suns. This means the sky above is not a single moment, but a layered tapestry of history, where every point of light tells a story from a different chapter in the grand cosmic novel. That deep blue marble you might see in artists' impressions is a world of pure fury. HD 189,733b is an exoplanet where the weather forecast is a permanent, violent storm of molten glass blowing sideways at unimaginable speeds. This planet's beautiful azure hue comes not from peaceful oceans, but from a hazy, scorching atmosphere rich in silicate particles. These are the tiny building blocks of rock and glass, and on this world they are caught in a perpetual supersonic tempest. Winds here are estimated to scream across the atmosphere at up to 8,700 kilometers per hour, a rate that makes the most powerful hurricanes on Earth feel like a gentle breeze. At such velocities, these silicate particles are not merely floating. They are whipped horizontally, creating relentless, scorching showers that shred anything in their path. The planet is tidally locked to its star, meaning one side is a permanent, broiling day, while the other is an eternal, slightly cooler night. This extreme temperature difference fuels the constant, violent winds that circumnavigate the globe. What would it be like to stand on this world? You would be instantly vaporized, but if you could somehow survive, you would witness a sky of glowing, molten sapphire, with a rain that doesn't fall but slices through the air like a blizzard of tiny, superheated daggers. This is not a place of liquid water or solid ground, but a crucible of elemental chaos, a stunning reminder that a planet's color can be a beautiful lie hiding a truly hellish reality. Our solar system itself is not a stationary arrangement of planets. It is a ship sailing through the galactic sea, and like any vessel moving through a medium, it leaves a wake. Streaming behind us for billions of miles is the heliotail, a vast and structured region that is the sun's own imprint on the galaxy. This is not a tale of light or dust, but one of energized particles, the final breath of the solar wind as it slows and mixes with the interstellar medium. For decades, this structure was purely theoretical, but NASA Interstellar Boundary Explorer, or IBEX, mission transformed it from an idea into a map. The spacecraft did not journey to the edge of the solar system. Instead, it remained in Earth's orbit, patiently collecting energetic neutral atoms that originated from this distant boundary. These atoms acted as cosmic messengers, and when their data was pieced together, it revealed a shape that surprised everyone. Rather than a simple, elongated trail, our solar system's tail resembles a four-leaf clover, with two lobes of slower-moving particles stacked above and below two lobes of faster-moving particles. This bizarre structure is a direct reflection of the Sun's own complex magnetic personality and the varying speeds at which it ejects material into space. The heliotail tells a dynamic story of our Sun's constant struggle against the galactic wind. It is the signature of our entire system's journey, a ghostly footprint in the cosmos that proves we are not just observers of the universe but active participants, carving our own unique path through the endless dark. Pluto's journey around the Sun is a marathon of almost incomprehensible duration. A single Plutonian year drags on for 248 Earth years, a slow, lonely circuit so vast that it has not even finished one complete orbit since its discovery in 1930. The tiny world, now classified as a dwarf planet, was spotted for the first time when it was in one region of its path, and it will not return to that same spot until the year 2178. This glacial pace is a product of its immense distance from the Sun and its highly elliptical or oval-shaped orbit. At its closest approach, Pluto ventures inside the orbit of Neptune, while at its most distant, it recedes into the deep freeze of the Kuiper belt. This dramatic in and out movement creates seasons of epic and violent transformation. When Pluto is nearer to the Sun, the slight increase in solar energy is enough to warm its surface, just enough to cause some of the frozen nitrogen, methane, and carbon monoxide on its surface to sublimate, turning directly from solid ice into a thin, tenuous atmosphere. For a brief period, this world has a sky, but this summer does not last. As Pluto continues along its elongated path, it slowly drifts back into the frigid depths. The tiny amount of heat it receives vanishes, and the temperature plummets toward absolute zero. the entire atmosphere, every molecule of gas does not just dissipate. It freezes out of the sky and snows back down onto the surface, covering the landscape in a fresh layer of exotic ice. The entire world essentially holds its breath for over a century, its atmosphere lying frozen solid on the ground, waiting for the distant promise of another spring. This cycle of atmospheric collapse and rebirth, playing out over centuries, makes Pluto not a static ball of ice, but a dynamic world with a climate as complex and cyclical as our own, just operating on a timescale that dwarfs human history. Our galactic core holds a flavor you might recognize from a bakery. Deep within the massive dust cloud known as Sagittarius B2, radio telescopes have identified a molecule called ethyl formate. This is the very same compound that gives raspberries their distinct fruity scent and is a key ingredient in the aroma of rum. How can we possibly know what a cloud of gas tens of thousands of light years away smells like? The answer lies in the cosmic fingerprinting technique of spectroscopy. Every molecule in the universe vibrates and rotates at its own unique set of frequencies. When light from a distant star passes through a cloud of gas and dust, these molecules absorb very specific colors or wavelengths of that light. By the time the light reaches our telescopes, it carries a barcode of missing lines, a unique signature that reveals the chemical identity of the substances it encountered. It is like hearing an orchestra play a chord and being able to pick out the precise note of a single flute. When astronomers pointed their instruments toward the galactic center, they saw the unmistakable barcode of ethyl formate imprinted on the starlight. This discovery creates a wonderfully whimsical bridge between the vast, impersonal cosmos and our most intimate human experiences. The heart of our swirling galaxy, a place of supermassive black holes and frenzied stellar birth, shares a chemical kinship with a summer fruit and a bottle of dark rum. It is a reminder that the universe is not just made of abstract forces and distant fires, but of the very same building blocks that create the flavors and fragrances of our own world. The cosmos is not only stranger than we imagine, it is strangely familiar. That galactic raspberry scent is a strangely intimate connection to the cosmos, yet other regions of space offer only profound emptiness. Lurking in the constellation of Boötes is one of the largest known voids in the universe, a spherical expanse of near-nothingness so vast it defies easy explanation. Known as the Boötes Void, this region spans an astounding 330 million light-years across. To grasp that scale, if you placed our Milky Way galaxy at one edge, it would be a single, lonely speck looking out into a darkness so immense it could contain thousands of galaxies, yet it holds almost none. Instead of the teeming metropolises of stars found elsewhere, this void is a cosmic desert, home to only a few dozen isolated galaxies where there should be thousands. For cosmologists, this presents a profound puzzle. The standard model of the universe suggests that matter should be distributed somewhat evenly, like froth on a cappuccino, with clusters and voids, but nothing on this staggering scale. The Great Void is an anomaly, a hole in the cosmic structure that seems too large to have formed naturally in the time since the Big Bang. How could such a nothingness come to be? One theory posits that many smaller voids simply merged over billions of years, their walls collapsing into one another to create a single, giant emptiness. Another, more speculative idea is almost too fantastic to consider. What if the void is evidence of an unimaginably advanced civilization, one that has harnessed the energy of entire galaxies? This concept, rooted in theoretical physics, suggests a Type 3 civilization on the Kardashev scale might build a structure like a Dyson sphere not around a star but around a galaxy, blocking its light from view. While there is zero concrete evidence for this, and natural explanations are far more likely, the sheer scale of the Boötes Void forces us to confront the limits of our understanding. It stands as a silent, dark reminder that the universe is under no obligation to make sense to us, and that its greatest mysteries may not be in the brilliant lights, but in the profound and empty spaces between them. The chemistry of life may wear a completely different face on a world like Titan. Saturn's largest moon is a frozen mirror of our own planet, complete with rolling hills, vast lakes, and flowing rivers, yet its very substance is alien. The liquid that defines Titan is not water, but a frigid blend of methane and ethane, falling as rain and pooling into seas that ripple under a hazy orange sky. This creates the only other known hydrologic cycle in our solar system, a slow, cold echo of the water cycle that shapes Earth. The Cassini-Huygens mission gave us our first intimate look at this strange world. The Huygens probe descended through Titan's thick, nitrogen-rich atmosphere, its cameras revealing a complex landscape of drainage channels and shorelines carved by liquid methane. When it landed, it touched down on a damp, sandy plain littered with icy cobbles, a surface with the consistency of wet clay. Orbiting above, the Cassini spacecraft used radar to peer through the opaque haze, mapping over 620,000 square kilometers of liquid, including the vast Kraken Mare, a sea larger than Earth's Caspian Sea. On Titan, the conditions are so cold, averaging -290 degrees Fahrenheit, that water is frozen solid, harder than granite. It is the methane that plays the role of water, evaporating from the lakes, forming clouds in the sky, and then drizzling back down to the surface in a slow, perpetual cycle. This raises a profound astrobiological question. Could life exist in these methane lakes? Water-based life, as we know it, would be impossible, but scientists speculate about the potential for exotic methane-based biochemistry. Instead of cells filled with salty water, organisms might use liquid methane as their internal solvent, with membranes made from flexible, nitrogen-based molecules. Their metabolism would be unimaginably slow, their life processes unfolding over centuries or millennia, adapted to a world where the very definition of a solvent is rewritten. Titan stands as a testament to nature's boundless creativity, proving that the processes we associate with a living world can be recreated with an entirely different set of ingredients, offering a second, parallel version of planetary geology and just maybe a second Genesis. Deep within the Sun's core, a continuous thermonuclear explosion rages. Every second of every day, our star transforms 600 million tons of hydrogen into 596 million tons of helium. The missing 4 million tons of mass does not simply vanish. It is converted directly into pure energy, an amount equivalent to detonating trillions of hydrogen bombs simultaneously. This is the relentless engine of nuclear fusion, the process that has illuminated our solar system for 4.5 billion years. The core is a crucible of unimaginable extremes, with temperatures soaring to 27 million degrees Fahrenheit and pressure more than 250 billion times greater than the air at sea level on Earth. Under these brutal conditions, hydrogen nuclei, which are single protons, are moving so fast that they overcome their natural electrical repulsion and slam into one another. They fuse, creating a new, heavier element, helium, and in that act of creation, a tiny amount of mass is annihilated, becoming energy as described by Einstein's famous equation. This energy does not rush straight to the surface in a beam of light. Instead, it begins a slow, arduous journey outward. First, as high-energy gamma rays, the energy is absorbed and re-emitted by the incredibly dense plasma of the Sun's inner layers. A single photon of light might take tens of thousands of years to zigzag its way from the core to the surface, constantly bumping into atoms in a random walk through the stellar interior. Once it finally reaches the surface or photosphere, this energy is released as the sunlight we see and feel. Every warm ray on your skin, every leaf grown through photosynthesis, is powered by this ancient, slow-moving energy, born in a stellar furnace at the heart of our solar system. This means the sunlight touching you today began its epic voyage long before the first human civilizations were even a dream. The glittering band of satellites encircling our planet is also a growing field of celestial shrapnel. Orbiting Earth at thousands of miles per hour are millions of pieces of space junk, from defunct satellites and spent rocket stages to flecks of paint and frozen coolant. Each fragment, no matter how small, carries the destructive potential of a bullet due to its immense velocity. This orbital graveyard poses a direct and escalating threat to the vital infrastructure we depend on every day. Global positioning systems, weather forecasting, international communications, and even the International Space Station all share this congested highway. The station has had to perform emergency maneuvers multiple times to avoid collisions with tracked debris, a high-stakes dance where a single mistake could be catastrophic. The real danger lies in a scenario known as the Kessler syndrome, a cascading chain reaction where one collision creates thousands of new fragments, each capable of causing further destruction, until a dense cloud of shrapnel renders entire orbits unusable for generations. In response, scientists and engineers are developing ingenious cosmic cleanup technologies. Proposed solutions include harpoons that could spear large pieces of debris, nets to ensnare them, and even lasers to nudge smaller fragments into a decaying orbit where they would safely burn up in the atmosphere. Some concepts involve magnetic tugs that would latch onto derelict satellites, or giant foam balls that would expand around junk to increase its drag. This is no longer a theoretical problem, but an urgent environmental crisis just a few hundred miles above our heads, a challenge we must solve to secure our future in the final frontier. The coldest place we know of in the entire universe is not in some distant, empty void, but right here in our own cosmic neighborhood. The Boomerang Nebula, a cloud of gas 5,000 light-years away, holds the record with a temperature of just 1 degree Kelvin above absolute zero. That is a single, fragile degree above the point where all atomic motion theoretically ceases. This is even colder than the frigid background glow of the Big Bang, which permeates all of space at nearly 3 degrees Kelvin. How can this nebula plunge to such a profound chill? The secret is its breathtaking speed. The aging star at its heart is expelling its outer layers at a ferocious rate, more than 10 times faster than our own sun's solar wind. This gas expands into the void so rapidly that it acts like a cosmic refrigerator. You can feel this principle on a small scale by blowing on your hand with your mouth wide open, which feels warm. Now purse your lips and blow. The air feels cooler because it is expanding more quickly as it leaves your mouth. The Boomerang Nebula is doing this on a stellar scale, its gas expanding so violently that it cools itself to a temperature lower than the empty space it is rushing into. We are witnessing a star's final breath creating a pocket of near-absolute stillness, a fleeting monument to cold that will eventually be warmed by the gentle, ancient heat of the universe itself. Drifting through the absolute cold and dark between stars are orphaned worlds, planets without a sun. These are rogue planets cast out from their home solar systems by gravitational chaos to wander the galaxy alone. Detecting these pitch-black nomads is one of astronomy's greatest challenges, since they emit no light of their own and have no star to illuminate them. Astronomers hunt for them using a cosmic quirk of gravity called microlensing. When one of these dark planets passes in front of a distant background star, its gravity acts as a tiny lens, bending and focusing the star's light for a brief moment. For a few hours or days, the star appears to brighten, betraying the invisible world's presence as it drifts silently by. This method suggests a staggering reality. These lonely wanderers may be incredibly common, with recent estimates proposing there could be trillions of them in the Milky Way, potentially outnumbering stars themselves. Imagine the landscape of such a world. Its surface would be a permanent, deep frozen night with no sunrise, no blue sky, and no concept of a year. The only light would come from the faint, unmoving gauze of the Milky Way above. Any atmosphere would likely have collapsed into a frozen crust, leaving a barren surface exposed directly to the vacuum of space. Yet, could there be a sliver of hope for life in such a desolate place? If a rogue planet retained a thick, insulating hydrogen atmosphere or possessed a hot, radioactive core, it might trap enough geothermal heat to maintain a vast subsurface ocean of liquid water sealed away beneath an icy shell. In that eternal darkness huddled around a planetary heart of warmth, life might find a way to persist, completely isolated and unaware of the universe outside. These dark, untethered worlds force us to expand our definition of a planet, transforming the interstellar voids from empty highways into potential homes for hidden, drifting biospheres. Even our own planet is slowly growing heavier. Each day, Earth gains tens of tons of mass, not from new mountains rising, but from a constant, gentle rain from the heavens. This is cosmic dust, microscopic fragments of asteroids and comets that have traveled for millions of years, only to meet their end as a fleeting streak in our atmosphere. These tiny particles, most no larger than a grain of sand, burn up as meteors, adding their vaporized mass to our world in an imperceptible but relentless accumulation. This celestial delivery service is so consistent that over a single year, it adds the equivalent mass of a large cargo ship to the planet. At the same time, our planet is also losing weight, but at a far slower rate. The very top of our atmosphere, a wispy region known as the exosphere, is so thin that the fastest-moving air molecules can achieve escape velocity, flying off into interplanetary space. Lightweight hydrogen and helium atoms are the most likely to make this great escape. Yet, the amount of atmosphere we lose this way is minuscule compared to the cosmic dust we gain. Earth is decisively winning the cosmic weight loss game, consistently packing on more pounds than it sheds. This slow, steady fattening has been happening for over 4 billion years, meaning a significant portion of the very ground beneath your feet was once stardust, delivered piece by piece from the depths of the solar system. Our world is not a closed system, but a living, breathing entity in a constant, silent exchange with the cosmos. The sun's calm face masks a violence that can unleash more energy than millions of hydrogen bombs in a matter of minutes. This is a solar flare, a catastrophic explosion on the sun's surface born from the intense stress of its own magnetic fields. Think of the sun's magnetic field as a vast web of invisible, twisted rubber bands. As the sun rotates, these bands of magnetic force can become tangled and strained, storing immense energy. When the tension becomes too great, they snap, reconnecting in a new, more stable configuration. This sudden rearrangement catapults a colossal amount of energy across the entire electromagnetic spectrum, from radio waves to powerful X-rays and gamma rays. The flash of extreme ultraviolet light from a major flare can reach Earth in just over 8 minutes, instantly battering the upper layers of our atmosphere. This surge of energy can ionize the atmosphere, abruptly degrading or even blacking out high-frequency radio communications used by aviation and emergency services. It is like a cosmic EMP, a pulse that scrambles the signals we depend on, but the storm is only beginning. Following the initial flash, a coronal mass ejection often erupts, a billion-ton cloud of magnetized plasma hurled into space at several million miles per hour. When this tsunami of charged particles reaches Earth a day or two later, it interacts with our planet's own magnetic field, compressing it and causing geomagnetic storms. These storms induce powerful electrical currents in long conductors like power grids, threatening to trip circuit breakers and cause widespread blackouts. They can also fry the delicate electronics of satellites, turning multi-million-dollar assets into silent, drifting junk. Yet from this celestial violence comes one of nature's most breathtaking displays. Those same particles, channeled toward the poles by Earth's magnetic field, collide with atoms of oxygen and nitrogen in the upper atmosphere, causing them to glow. The result is the aurora, a shimmering curtain of green, red, and purple light that dances across the polar skies. A single flare, therefore, is a duality of creation and destruction, a reminder that the star that gives us life also holds the power to disrupt our fragile technology with a single, furious breath. Our own moon still trembles with a hidden geological life. The Apollo astronauts left behind seismometers that recorded thousands of subtle shudders, proving our celestial companion is far from a silent, static sphere. These moonquakes come in several distinct varieties, each telling a different story about the forces still at work. Deep below the surface, roughly 700 kilometers down, the most common type rumbles to life. These deep moonquakes are triggered by the relentless gravitational tug of war with Earth. As our planet pulls on the moon, it creates tidal stresses that flex and strain the lunar interior, causing it to crack and shift in a regular, predictable rhythm. Then there are the shallow moonquakes, which originate just a few dozen kilometers beneath the dusty regolith. These are far more powerful and mysterious. Scientists believe they are caused by the moon's extreme temperature swings. For 2 weeks, the surface bakes in relentless sunlight, with temperatures soaring to 260 degrees Fahrenheit. This intense heat causes the crust to expand. Then, during the 2-week-long lunar night, the temperature plummets to 280 degrees below zero, forcing the rock to contract violently. This endless cycle of expansion and contraction over billions of years has created global stress, and the crust occasionally releases this pent-up energy in a sudden, sharp tremor. Some of these shallow quakes have registered up to 5.5 on the Richter scale, strong enough to shift boulders and rearrange the landscape. This ongoing activity reveals a world that is cooling and settling, its rocky shell still creaking and groaning as it adjusts. The moon is not the geologically dead relic we once thought. It is a world with a faint, cold heartbeat, a subtle vibration that echoes the dynamic history of our entire Earth-Moon system. The very fabric of reality might be a grand and complex illusion. A startling theory emerging from the frontiers of theoretical physics proposes that our universe, in all its three-dimensional glory, could be a hologram. This is not a metaphor from science fiction, but a serious mathematical proposition known as the holographic principle. It suggests that all the information needed to describe everything within a volume of space, every star, every planet, every one of us, can be encoded on a two-dimensional surface that surrounds it like a cosmic DVD. Imagine watching a breathtakingly realistic movie on a flat screen. The image appears to have depth with characters moving toward you and away, yet you know it is all contained on a two-dimensional surface. The holographic principle posits that our universe operates in a similar way. The world we experience, with its rich textures and tangible solidity, might be a projection from a vast, two-dimensional shell at the very edge of the cosmos. This idea finds its roots in the study of black holes. Physicists discovered that the maximum amount of information a black hole can contain is not proportional to its volume, but to the surface area of its event horizon. This was a profound clue that the fundamental description of space might reside on its boundary, not within it. If this is true, the implications are staggering. It would mean that the three-dimensional world is an emergent property, a consequence of information processing happening on a distant, flat surface. Your perception of moving through a solid room, feeling the weight of an object in your hand, could be the result of an unimaginably complex calculation occurring at the universe's outer limit. This does not make our reality any less real, but it fundamentally redefines what real means. It hints that space, time, and gravity themselves might not be fundamental, but secondary phenomena that arise from a deeper, more abstract layer of information. The universe, then, is not just stranger than we imagine, but its very structure may be a magnificent shadow play, a holographic echo from the edge of existence. The serene twinkling of stars often hides a predatory dance in the dark, Far from being solitary beacons, many stars exist in close binary systems, locked in a gravitational embrace where one can slowly consume the other. The vampire is typically a dense stellar corpse, a white dwarf or a neutron star, while its victim is a larger, more bloated companion. Their intimate orbit allows the dense remnant's immense gravity to reach out and siphon away the outer layers of its neighbor's atmosphere. This stolen gas does not simply vanish. It spirals down onto the surface of the predatory star, forming a blazingly hot, swirling disk of accretion. For a white dwarf, this theft can have spectacularly violent consequences. The accumulated hydrogen on its surface builds in pressure and temperature until it ignites in a runaway thermonuclear explosion. This is a nova, a brilliant flash that can make a faint star visible to the naked eye for a brief, glorious period. The star is not destroyed, and the cycle often repeats, with the vampire star returning to its feast, setting the stage for another outburst in the future. But if the white dwarf is particularly greedy and accumulates enough material to push it over a critical mass threshold, something far more cataclysmic occurs. The entire star can be obliterated in a Type Ia supernova, an explosion so uniform and so incredibly bright that it can outshine an entire galaxy. These stellar fireworks are cosmic measuring sticks, allowing astronomers to gauge vast distances across the universe. This relationship transforms the peaceful concept of a binary system into a dramatic story of cosmic theft and inevitable, shattering payback, where the life of one star fuels the spectacular death of another. Our galaxy is not a rigid pinwheel, but a fluid and ever-changing river of stars. While we speak of the Milky Way's collision with Andromeda in the distant future, our own solar system is already on a slow-motion journey through the galaxy's shifting architecture. The beautiful spiral arms we see in illustrations are not permanent structures made of the same stars, but rather they are like cosmic traffic jams. These are density waves, regions where stars and gas pile up as they orbit the galactic center at different speeds. Imagine a wave moving through a crowded stadium. The people stand up and sit down, but the wave itself travels around the arena. Similarly, stars drift in and out of these spiral arms as they journey around the galaxy. Our Sun, along with its planetary family, is currently cruising through a relatively quiet region called the local arm, but this is a temporary residence. Over spans of millions of years, our entire system will slowly migrate, eventually passing through a much denser spiral arm. What would that transition be like? The night sky would gradually transform. The familiar constellations would stretch and distort, their patterns dissolving as new, brighter stars from the arm's rich stellar nurseries flood into view. The celestial backdrop would become far more crowded and brilliant. This journey through a spiral arm would not be without its perils. These regions are packed with giant molecular clouds, the birthplaces of massive stars. These stellar infants live fast and die young, exploding as supernova relatively close by. While the distances are still vast, a nearby supernova could bathe our solar system in intense radiation, with potential consequences for our planet's atmosphere. This cyclical journey, repeated every couple of 100 million years, suggests that Earth has likely passed through these turbulent neighborhoods before, each transit leaving a faint geological signature in the deep past. Our place in the galaxy is not fixed but nomadic, and the cosmic neighborhood we call home is in a state of perpetual, graceful evolution. Floating around a supermassive black hole 12 billion light-years away is the largest and most distant body of water ever detected. This is not a liquid ocean, but a colossal reservoir of water vapor, a cosmic fog holding 140 trillion times all the water in every ocean on Earth. The sheer scale of this discovery is almost impossible to grasp. If you could somehow gather every drop of water on our planet, from the deepest ocean trenches to the polar ice caps, and then multiply that volume by 140 trillion, you would begin to approach the sheer quantity of water suspended in that single region of space. This vast cloud is powered by a brilliant quasar, the energetic core of a young galaxy, where the central black hole is actively feeding and blasting out immense energy. The water vapor exists in the surrounding galactic disk, a maelstrom of gas and dust spiraling inward. This finding fundamentally rewrites the timeline of water in the cosmos. Because this light has taken 12 billion years to reach us, we are seeing the universe as it was when it was only 1.6 billion years old. This proves that water, one of the essential ingredients for life as we know it, was already abundant in the universe's relative infancy. It did not take billions of years for complex molecules to slowly accumulate. The raw elements of hydrogen and oxygen were forged in the hearts of the first stars, and as those stars died in supernova, they seeded the cosmos with the building blocks for water. Wherever conditions were right, in the dense, warm disks around young black holes or in the nurseries of new stars, these atoms found each other and combined on a truly epic scale. This invisible ocean tells us that water is not a rare or special substance. It is a common and pervasive feature of the universe, a fundamental part of the cosmic landscape from almost the very beginning. The next time you take a sip of water, remember that you are tasting a substance as ancient as the stars themselves, a legacy written in vapor across the depths of time and space. That final sip of ancient cosmic water connects us to a universe of strange transformations, some of which affect the human body itself. Astronauts returning from the International Space Station often come back literally taller than when they left. In the persistent microgravity of orbit, the constant downward pull of Earth vanishes and the spine is freed from its lifelong compression. The vertebrae, those small bones stacked in a column, are no longer being squeezed together by gravity's weight. They gently separate and expand, allowing the cartilage discs between them to decompress and swell with fluid. This subtle uncoiling can add up to 2 full inches to a person's height, a temporary growth spurt of up to 3%. Imagine the sensation of your body quietly stretching, of your joints and ligaments adjusting to a new, more elongated frame without a single conscious effort. This newfound height, however, is not without its consequences. The lengthening spine can tug on the muscles and nerves of the back, often causing significant discomfort and pain for crew members as their bodies adapt. The real challenge arrives when they return home. As their spacecraft plunges back into Earth's thick atmosphere and gravity reasserts its familiar dominance, the process brutally reverses. The spine is compressed once more, squeezing back into its original dimensions over a period of days or weeks. This recompression is often more painful than the initial expansion, a stark reminder that our bodies are fine-tuned for a specific gravitational environment. This cosmic height change is a profound illustration of our physical connection to the planet we call home, a bond so fundamental that leaving it literally reshapes us from the inside out. Your sense of direction would mean nothing in the deep void between galaxies. The comforting idea of north, a fixed point on our compass, dissolves completely in the vacuum of space where there is no universal up or down. Astronomers still need maps, of course, so they create artificial poles for every planet and moon, defining a north based on the object's rotation. For the starscape itself, they use a celestial sphere, a giant imaginary globe projected onto the sky, with its own north pole pointed near the star Polaris. But these are just useful conventions, not fundamental truths. Your true orientation is always relative, completely dependent on your frame of reference. If you are floating near a spacecraft, your up might be toward its cockpit. For someone inside, down is toward the floor. If you were to flip over, your entire universe would instantly reorient, and what was once above you would now be below. This relativity extends to the grandest scales. A galaxy millions of light years away might appear to be spinning upside down from our perspective, but for an observer within that galaxy, their spiral arms would sweep through a sky that feels perfectly upright. There is no preferred direction in the cosmos, no master compass pointing to a single, true north. Every traveler, from an astronaut to a distant star, carries their own personal sky, a private map where they are always at the very center. The moon's far side is often mistakenly called the dark side, yet it basks in just as much sunlight as the side we see. Our view is fixed because the moon is tidally locked to Earth, its rotation perfectly synchronized with its orbit. From our perspective, it appears to turn only once, keeping one face forever turned away from us. This hidden hemisphere remained a complete mystery until the first lunar orbiters captured its image in the 1960s, revealing a world startlingly different from the familiar face we know. Where the near side is marked by vast, smooth maria of ancient lava, the far side is a rugged, crater-pocked landscape dominated by one of the most colossal scars in the solar system. The South Pole Aitken Basin is an impact crater so immense it spans nearly a quarter of the lunar surface, a depression deep enough to swallow mountains. This feature is a frozen record of a primordial cataclysm, a blow so powerful it is thought to have excavated material from the moon's very mantle. Why the two sides are so different remains an active puzzle. One leading theory suggests the moon's crust is thicker on the far side, making it harder for magma to well up and form the smooth plains that characterize the Earth-facing hemisphere. This hidden landscape, illuminated by sunlight but never by Earth's glow, holds secrets to the violent early history of our entire Earth-Moon system, a stark reminder that even our closest companion still guards profound mysteries just out of sight. The universe, in its ultimate summary, is not a deep, majestic black nor a brilliant, fiery blue. Its true color is a soft, warm beige, a shade astronomers officially call cosmic latte. This was not a guess, but the result of a monumental census in 2002, when scientists combined the light from over 200,000 galaxies, blending their countless stars into a single, average hue. This cosmic paint chip reveals a profound story about the stellar population of our cosmos. The color of starlight is a direct indicator of its age and temperature. Young, massive, and immensely hot stars burn with a fierce blue-white intensity. They are the brilliant, short-lived giants of the galaxy. Older, smaller stars, like our own sun, glow with a more moderate yellow-white light. The most ancient and common stars in the universe, the red dwarfs, are cool and dim, radiating most of their energy in the red part of the spectrum. When you mix all these stellar colors together, the vibrant blues and the deep reds cancel each other out, leaving a gentle, off-white tone leaning slightly toward beige. The prevalence of this particular shade of white tells us that the universe is currently in a middle age, dominated by these older, yellowing stars. The era of rampant blue star formation, the universe's brilliant and violent youth, has largely passed. We live in a cosmos painted in a calming, creamy white, a quiet and mature phase where the most common light is the gentle glow of aging suns. So, the next time you look at the night sky, remember that the overwhelming impression when everything is added together is not one of darkness but of a vast, comforting cup of cosmic latte. This familiar daily rhythm makes Mars the most Earth-like world we know in terms of time. A single day on the red planet, called a sol, lasts just 24 hours and 39 minutes. That extra half hour is a trivial difference over the course of a day, but it has profound implications for any future human presence. Our own biological clocks, the circadian rhythms that dictate when we sleep and wake, are finely tuned to a 24-hour cycle. A day on Mars is close enough that our bodies could likely adapt with relative ease, perhaps just requiring a slightly later bedtime each evening. This natural compatibility is a stroke of cosmic luck, removing one of the biggest physiological hurdles to living on another world. Imagine not fighting a brutal 6-hour jet lag every single morning, but instead settling into a daily routine that feels almost like home. This temporal kinship directly influenced the engineers who designed the Martian rovers. These robotic explorers operate on a Sol-based schedule. Their teams on Earth live on Mars time for the duration of their missions, their workdays shifting 39 minutes later each day, slowly drifting through our day and night. They do this to be awake and working when the rovers are in daylight, maximizing the science that can be done. For humans, this gentle daily stretch means that a standard clock would still be useful, with only a minor adjustment to the length of an hour or simply adding an extra 39 minutes to the end of each day. This small detail makes the monumental challenge of building a new society on Mars feel just a little more possible, as if the planet itself is offering a welcoming, familiar rhythm to those brave enough to answer its call. A world might exist where the very idea of a coastline is an alien fantasy. Orbiting a dim red star 40 light-years away is GJ 1214b, a super-Earth completely enveloped by a global, bottomless ocean. This is not a planet with seas and continents, but a true water world, a sphere of liquid with no land in sight from pole to pole. Its entire surface is a single, unbroken expanse of water, thousands of miles deep, resting upon a core of solid, high-pressure ice and rock. The pressure in those abyssal depths would be unimaginable. As you descend, the weight of the water above you would build to millions of times the pressure we experience at sea level. This immense force would compress the water itself into exotic forms of ice, not because it is cold, but because the pressure forces the molecules into a crystalline structure. You would find layers of Ice 7 and Ice 10, strange hot ices that form at temperatures of hundreds of degrees, a solid phase of water created by force alone. In this perpetual, sunless deep, the chemistry for life would follow a completely different path. On Earth, life clusters around hydrothermal vents on the seafloor, where mineral-rich water provides energy. On a world like GJ 1214b, the entire planet could be one giant, churning chemical reactor. The immense pressure could allow for the formation of complex organic molecules in the deep, while the upper layers, exposed to the faint starlight, might host a different kind of biology. Any life here would be truly aquatic, forever drifting or swimming through a universe of liquid, unaware that anything called air or land could ever exist. This potential for a hidden, global biosphere challenges our Earth-centric view of habitability, suggesting that the most common cradle for life in the cosmos might not be a rocky world like ours, but a boundless, dark ocean beneath an endless sky of water. Our entire galactic neighborhood is being pulled toward a phantom in the dark. Lying in the direction of the constellation Centaurus, some 250 million light-years away, is a gravitational anomaly so powerful it is drawing our Milky Way and thousands of other galaxies toward a single, unseen point. Astronomers call this cosmic focal point the Great Attractor, and its true identity remains one of the most perplexing puzzles in modern cosmology. We are rushing toward it at a staggering 14 million miles per hour, yet we cannot clearly see what awaits us. The heart of our own galaxy blocks the view. The Milky Way's equatorial plane is thick with gas and dust, creating a zone of avoidance that obscures nearly a third of the visible universe beyond, including the precise center of this immense gravitational pull. It is like trying to see a distant city while standing in a dense, perpetual fog. Early observations could only detect the motion, the undeniable river of galaxies all flowing in the same direction, hinting at a mass equivalent to tens of thousands of Milky Ways. What could possibly possess such gravitational authority? Initial theories proposed a single, enormous concentration of mass, a previously unknown galactic supercluster. As our ability to peer through the obscuring dust improved, a clearer picture began to emerge. We now know the Great Attractor is not the final destination, but a waypoint on a much grander cosmic journey. The true source of the pull lies even farther beyond, in an immense structure known as the Shapley supercluster, the largest known concentration of matter in our local universe. Yet the mystery has only deepened. The sheer number of galaxies in the Shapley supercluster cannot fully account for our motion. There seems to be even more mass, invisible and unexplained, woven into the cosmic web in that direction. This suggests the great attractor is not a single object, but a colossal knot in the fabric of the universe, a junction where filaments of dark matter and countless galaxies converge, creating a gravitational well of unimaginable scale. We are not just falling toward a hidden giant, we are being swept along in a current that flows toward the largest structures in existence, a silent river in the cosmos whose ultimate source we are still struggling to see. Even the deepest voids between galaxies are not perfectly empty. Space is an excellent vacuum, far better than any we can create on Earth, but it is not an absolute nothingness. If you were to take a typical cubic meter of interstellar space, it would contain only a handful of atoms, mostly hydrogen, drifting in the dark. This is the interstellar medium, the thin, raw material from which everything is born. To us, this seems like an impossible emptiness, but on a galactic scale, this sparse gas and dust is the fundamental stuff of creation. All the stars you see, every planet, and even your own body, were once part of this cosmic haze, gathered together over billions of years by the patient, relentless pull of gravity. This medium is also threaded with radiation, the faint afterglow of the Big Bang, and haunted by the invisible presence of dark matter and dark energy, which shape the cosmos even though they do not interact with light. When a region of this medium becomes dense enough, it can collapse under its own weight, spinning and heating until nuclear fusion ignites and a new star is lit. The planets then form from the leftover dust and gas swirling in a disk around that infant sun. We are all, in the most literal sense, made from stardust, but before that, we were the quiet atoms of the interstellar medium, waiting in the dark for our turn to shine. This profound connection means that the seeming emptiness of space is not a barren void, but a cosmic womb, a reservoir of potential holding the ingredients for future suns and worlds, a silent promise of creation written in the spaces between the light. That final thought, that the void is a cosmic womb, is not just a beautiful concept, it is your own origin story. Nearly every atom that makes up your body, with the single exception of hydrogen, was forged in the heart of a star that died long before our sun was even born. The iron in your blood that carries life-giving oxygen, the calcium that strengthens your bones, the carbon that forms the backbone of your very DNA, all of these were created under immense pressure and temperature inside a stellar furnace. When that ancient star reached the end of its life, it did not fade quietly. It erupted in a cataclysmic supernova, a titanic explosion that blasted these newly forged elements out across the galaxy. For billions of years, this stardust drifted through the interstellar medium, that cosmic haze we just discussed, eventually coalescing into the cloud that would become our solar system, our Earth, and ultimately you. This means that when you look up at the night sky, you are not just a distant observer. You are the universe looking back at itself. The carbon in your hand was once part of a red giant, the oxygen you breathe was expelled by a dying star, and the gold in a piece of jewelry was likely formed in the violent collision of two neutron stars. We are not simply in the universe is in us. This profound connection ties your existence directly to the grand cosmic cycle of birth, death, and rebirth. It is a humbling and empowering truth, a final fact that transforms the 50 wonders we have explored from distant curiosities into chapters of your own epic history. You are, in the most literal sense, made of stardust, and that makes you a permanent part of this endless, beautiful story. Our journey through these 50 cosmic wonders reveals a universe that is stranger, more violent, and infinitely more beautiful than any fiction. We have wandered from the crushing density of neutron stars to the silent, drifting oceans of rogue planets, from the hellish rain of molten glass to the gentle beige glow of the cosmos itself. This tapestry of facts underscores the breathtaking scales of space and time, where a single day can outlast a year and a footprint can outlive civilizations. More than anything, these discoveries illuminate a profound interconnectedness, binding the iron in our blood to the heart of an ancient, exploding star. The next time you step outside and gaze at the night sky, remember that you are not just looking at distant points of light. You are witnessing a dynamic, ever-changing story of which you are an intrinsic part. We would love to hear which fact reshaped your perspective the most, so share your favorite in the comments below. If your curiosity for the cosmos has been ignited, subscribe for more journeys that explore the deepest mysteries of our incredible universe.